Hello everyone, this video is over lesson number 10 and will focus on learning goals 3 to 7 where we'll talk about the three temperature scales and the difference between them. We'll solve problems converting temperature from one unit to another. We'll talk about the concept of specific heat and its units, and we'll explain the relationship between substance specific heat and thermal conductivity, and we'll solve problems that involve heat exchange. Now, in terms of temperature, temperature is a measure of the kinetic energy, the thermal kinetic energy of the molecules inside the matter. We learned in lesson number 8 that thermal kinetic energy is type of kinetic energy. When you heat any object, you are increasing the motion of its particles. You are increasing the kinetic energy of the particles inside that object. And the measure of this kinetic energy of the heated molecules is temperature, specifically the Kelvin scale. So it's very important to understand the temperature scales. Now, if we look at the temperature scale here, and let's compare between the two famous scales, the Fahrenheit and Celsius, and let's look at the freezing point and the boiling point of water. Notice that in the Celsius scale, the freezing point of water is 0 degrees Celsius, while in Fahrenheit it's 32 Fahrenheit, while the boiling point of water is 100 degrees Celsius, in contrast to 212 Fahrenheit. So here, if you notice in terms of increments, we have 100 increments between the freezing point and the boiling point of water in the Celsius scale, while we have 180 increments for the same interval in Fahrenheit. Now, what does that tell you about the gap between one increment and the next in the Fahrenheit compared to the Celsius? Since we have to fit 180 increments in the same gap here for Fahrenheit, then the interval between one increment and the next should be shorter than that in the Celsius scale. And the ratio is 180 to 100, which is 9 to 5. 180 over 100 is 9 to 5. So the ratio here is 9 to 5. So this is one factor we have to take into consideration when we convert between Celsius and Fahrenheit. We have to take into consideration the interval that represents the gap between one increment and the next. In the case of Celsius, it's bigger than the Fahrenheit by a ratio of 9 to 5. So when you go from Celsius to Fahrenheit, you have to take this ratio into consideration. So you have to multiply the temperature in Celsius by 9 over 5. And then the other factor is the starting point. We can see here that the freezing point of water is 0 degrees Celsius compared to 32 Fahrenheit. So we have to add this 32 factor here in order to convert any temperature from the Celsius scale to the Fahrenheit scale. And we can use this equation to derive an equation to convert the Fahrenheit to Celsius. So you have to subtract 32 from both sides of the equation, then multiply 5 over 9 by both sides of the equation, and this will give us this equation here for converting Fahrenheit to Celsius. So we have the equation of converting Celsius to Fahrenheit, and then we have the equation of converting Fahrenheit to Celsius. Okay, now how about the Kelvin scale? Now, Kelvin scale follows the Celsius scale in terms of the gap between one increment and the next. And we can see that from the boiling and the freezing point of water. The freezing point of water in Celsius is 0, while in Kelvin it's 273. The freezing point of water is 100 degrees Celsius, which is equivalent to 373 Kelvin. So we can see that the Kelvin, as the case with Celsius, has 100 increments gap between the freezing and the boiling point of water. So we don't have problem in terms of increment to increment ratio, but the starting point here is 273 for the freezing point of water compared to 0 degrees Celsius. So basically, when you want to convert from Celsius to Kelvin, you have to add 273 to the temperature in Celsius in order to convert it to Kelvin. And vice versa, if you want to convert Kelvin to Celsius, and let's make sure this is uppercase K, you have to subtract 273 from the Kelvin temperature in order to convert it to Celsius. To go from Fahrenheit to Kelvin, you have to go through the Celsius. So you have to convert the temperature from Fahrenheit to Celsius first, then you can convert it from Celsius to Kelvin. Now the question is, why the freezing point of water is 273 Kelvin? Actually, the scale in Kelvin is based on the absolute zero, and absolute zero is the minimum temperature you can ever reach. You cannot go beyond 0 Kelvin. Meaning at 0 Kelvin, the molecules and the particles inside the matter will freeze. It will not move. As we said earlier, temperature is a measure of the thermal kinetic energy of the particles and molecules inside the matter becomes 0. So everything freezes, including atoms, molecules, and subatomic particles. And this 0 Kelvin is equivalent to negative 460 Fahrenheit, which is equivalent to negative 273 degrees Celsius. So that's the basis of the Kelvin scale. It's based on the absolute zero, which is the minimum temperature you can ever reach. You cannot go beyond 0 Kelvin because already matter has reached its minimum kinetic energy. Okay, after we talked about the temperature scales, we need to talk about the concept of heat transfer and what we mean by specific heat. As we mentioned, temperature is a measure of the average kinetic energy of the particles inside a substance, the molecules inside a substance. Heat, on the other hand, is energy that is in transit, meaning it's the amount of energy that is transferred between two objects when they have difference in the temperature. When you have two objects in contact, heat will always transfer from the object that has higher temperature to the object that has lower temperature. So when you place a piece of metal, assuming its temperature is 100 degrees Celsius, inside a cup that has cold water, assuming the initial temperature of the water is 21 degrees Celsius, the difference in the temperature between the metal and the water will cause heat to transfer from the object that has higher temperature to the object that has lower temperature. As long as they are in contact, the heat will continue transferring until they reach what we call it thermal equilibrium. At the thermal equilibrium point, all objects in contact will have the same final temperature, and the heat lost by the hot object is equal to the heat gained by the cold object because energy is conserved. Now let's look at the factors that affect the heat exchange. Now suppose you have a hot plate, a hot surface, and on this hot plate you place two beakers, and both beakers have the same amount of water. And let's say the initial temperature of both liquids is 20 degrees Celsius. That's the initial temperature of both liquids. Now let's say you want to increase the temperature of the first beaker from 20 to 22 degrees Celsius, while the other one you want to increase its temperature from 20 degrees Celsius to 24. Which one you should give more heat? Of course, the more you want to raise the temperature, the more the heat required to cause that change. So the first factor that heat exchange depend on is the change in the temperature, delta T. And the bigger the change, the more the heat. So increase of 4 degrees Celsius require double the heat of an increase of 2 degrees Celsius. So you need to give the speaker twice the heat in order to raise its temperature twice the other beaker. So that's the first factor, the change in the temperature. The other factor is the mass. So let's assume we have the same hot plate. Suppose we place in the first beaker 50 grams of water, while on the other beaker we placed 100 grams of water. So that's twice the mass. And let's say the increase in the temperature that we want to cause is the same. So we want to take the first water here from 20 to 22 degrees Celsius, and we need to cause the same change on the other beaker, meaning from 20 to 22. So delta T now is a constant. In both cases, we want to increase the temperature by 2 degrees Celsius. But the mass is different. One of them is 100 grams, the other one is 50 grams. So which one will require more heat in order to cause the same change in the temperature? And the answer is, and that's part of the experiment you'll do at home, you'll see that the 100 grams will require twice the heat, meaning you need to leave it on the hot plate twice the time compared to the 50 grams. So that's the other factor that will influence the heat exchange, the mass of the object. The bigger the mass, the bigger the heat exchange. So if you double the mass, you need to double the amount of heat given to that matter. So 100 grams will absorb twice the heat of 50 grams in order to cause the same change in the temperature. Now finally, and that's the important part that the heat depends on, is the type of matter you have. And this is what we call the specific heat. So for example, if we have the same hot plate, and now instead of water only, we have water and mercury. And let's assume we have the same amount. For example, 100 grams of water, H2O, and here we have 100 grams of mercury. So the mass is the same, hence the mass is a constant. And let's assume we want to cause the same change in the temperature. We want to increase the temperature of water from 20 degrees Celsius to 25 degrees Celsius. And we need to do the same thing for the mercury. So the change in temperature is constant, and the mass is constant for both of those two objects. Now, which one do you think will require more heat? Mercury or water? Or do they require the same heat since they have the same mass and they will undergo the same change in the temperature? And the answer is mercury actually will require much less heat than water. Water will require 40 times, almost 40 times more heat to cause the same change in the temperature for the same mass. And this depends on something called specific heat value. If we look at the specific heat of water, it's 4,187 joule per kilogram Celsius, while the specific heat of mercury is 138 joule per kilogram Celsius. So it's almost difference of 40 times, almost 40 times. Now if you look at this value, what does it mean? 138 joule per kilogram Celsius. So if you write this equation here, heat exchange equal to the change in the temperature times the mass times the specific heat. So heat H is equal to the mass times C, which is the specific heat, times the change in the temperature. Hence, specific heat is equal to the heat exchange divided by the mass times the change in the temperature. So the unit of the specific heat is unit of heat, which is unit of energy, divided by unit of mass, divided by unit of temperature. So it's joule per kilogram Celsius. And this value, the 138 joule per kilogram Celsius, this means that you need to give mercury 138 joules per 1 kilogram in order to cause 1 degrees Celsius increase in its temperature. And the same thing for water, 4,187 joule per kilogram Celsius. It means that you need to give a 1 kilogram mass of water 4,187 joules in order to change its temperature by 1 degree Celsius. So you can see here, the bigger the specific heat, the more you need to give heat to the matter in order to change its temperature. So specific heat is measure of thermal insulation, meaning how much the temperature of the matter is resistance to the heat exchange. The bigger the specific heat, the more its temperature will resist the heat exchange. So it's not easy to heat water. Water has very high specific heat, 4,187. So you need to give it 40 times more heat than mercury in order to cause the same change in the temperature. While mercury is very good thermal conductor, because its temperature is very sensitive to the heat exchange. You need to give it small amount of heat and you'll see rapid change in its temperature. And that basically tells us about what heat exchange depends on. And this tells us also about the concept of specific heat. Specific heat is like a fingerprint of materials, where you can see in this table the value of specific heat of different materials. You can see water is significantly higher than the others, 4,186 joule per kilogram Celsius, while metals in general have low specific heat. You can see here mercury is one of the lowest, 138. And mercury is a liquid. That's the special thing about mercury. It's the only metal that is liquid at room temperature. And that's why it's used, or it's used to be used in thermometers, because its temperature is very responsive to heat exchange. And there are many implications to the high specific heat of water. That's why water mainly is used as a coolant. Water is used in cars to lower the temperature of the engine, so it can absorb a huge amount of heat from the engine without big change in its temperature compared to the drop in the temperature of the engine. And if you go back to this example here, when you place this hot metal inside cold water, this metal has very low specific heat, while water has very high specific heat. And since the heat exchange is the same, meaning the amount of heat lost by the metal is equal to the heat gained by the water, what do you think will happen to the final temperature of the metal and the water? Will it be close to 100 or will it be close to 21? Since the temperature of object that has low specific heat is very sensitive to the heat exchange, meaning the temperature will drop rapidly, this object here that started with 100 degrees Celsius will most probably end up with something like 26 degrees Celsius as its final temperature when it reaches the thermal equilibrium, while the water temperature will be also 26 degrees since the final temperature will be the same for both of them. So you can see that this object went through big change in the temperature. Its change in temperature is 100 minus 26, which is around 74 degrees Celsius change in the temperature, while the cold water went from 21 to 26, so that's a change in the temperature equal to around 4 degrees Celsius. And that's a huge difference in the change in temperature. Makes sense because water has high specific heat, so its temperature is very resistive to the heat exchange, while metals have low specific heat, so their temperature is very sensitive to the heat exchange. Okay, and we saw like in the case of mercury, it's 40 times difference in the specific heat between mercury and water. In the case of metals like copper, it's around 12 times bigger. The specific heat of water is 12 times bigger than the specific heat of copper. Or iron, if we think in terms of the engine of the car, which is made of steel, which is a combination of iron and carbon. So we expect that the engine of the car will undergo a very big change in the temperature compared to the amount of heat gained by the water in your radiator. So that's why water is very good coolant. It can absorb a huge amount of heat with very small change in the temperature as we see here. And that's why like San Francisco or Miami, They undergo very small change in the temperature between summer and winter because water, the huge body of the water in the ocean, will absorb all the heat during summertime, and during winter time, the water will be still losing some of those heat to the atmosphere. And that's why also when you cook pizza or a pie, when you place it in the oven, all the parts of the pizza, which include the cheese and the crust, let's focus on the cheese and the crust, will reach thermal equilibrium, so they will have the same temperature. Now, when you get it out of the oven, which one will cool first? Is it the cheese or the crust? As you know from your experience, crust will cool first. And this is because cheese has huge amount of water, so it has high specific heat, while the crust will have low specific heat. An object with low specific heat has a temperature that is very sensitive to the heat exchange. So the temperature of the crust will drop rapidly, while the temperature of the cheese will drop slowly because of high specific heat of the cheese due to the water content of it. And the unit of specific heat, as you saw from the table, is joule per gram Celsius or joule per kilogram Celsius. But in general, it could be any unit of energy over unit of mass over unit of temperature. Hope this video clarified the concept of heat exchange and the meaning of specific heat value. Let me know if you have any questions over this video. Thank you.